Hello and welcome to another video on proof for A-level maths. Today we're looking at the proof that there's an infinite number of prime numbers. A natural starting point is to ask, what are prime numbers? And we might answer numbers like 2, 3, 5, 7 and so on. Another natural question is, how do we test if a number is a prime number? Is, for instance, 59 a prime number? To test it, we would try dividing by the first few prime numbers. Divide by 2 and we have a remainder of 1. Divide by 3 and we have a remainder of 2. Divide by 5 and we have a remainder of 4. Divide by 7 and the remainder is 3. There's no need to try 11, 13 and so on, as we know that the square root of 59 must be between 7 and 8, and 11 is beyond the halfway point, it's beyond 8. So we found that 59 has no prime factors, which means it's a prime number. Back to our proof. Our proof is a proof by contradiction. We assume the number of prime numbers is finite, which means there must be a largest prime number. Now just suppose Fred comes along and says, there are only 4 prime numbers, 2, 3, 5 and 7. We could say, hang on a minute, Fred. Take a look at this number, where we multiply all your prime numbers and then add 1. Let's call it n. Now either n is a prime number or it's not a prime number. As it's not on Fred's list, according to Fred, it can't be a prime number, which means it must have factors. 2 of the prime numbers on Fred's list must divide into it. So we could invite Fred to divide n by 2 and see what happens. We get a remainder of 1. And then we say divide it by 3. Again we get a remainder of 1. And then divide it by 5. Same again, a remainder of 1. And divide it by 7. Again, a remainder of 1. In other words, none of Fred's 4 prime numbers is a factor of n, which means one of 2 things. Either n is another prime number, or there's another prime number not on Fred's list that is a factor of n. Either way, there are more prime numbers than the 4 on Fred's list. Now that is a simplified version of our proof. We start by assuming the number of primes is finite. Let's call them P1, P2, P3, all the way up to Pn. That is to say, there are n prime numbers. Obviously, the first P1 is the number 2, P2 is 3, and so on. Now consider n, the product of all those prime numbers plus 1. If we divide n by P1, we'll get a remainder of 1. And the same will happen with P2 and P3 and with all our prime numbers. Each time we will get a remainder of 1. So none of our primes is a factor of n, which means one of 2 things. Either n is a prime number, or there's another prime number not in our list that divides into n. Either way, we have a contradiction. Our assumption must be false. The number of prime numbers must be infinite. And that's our proof.